Okay, let's start, everybody. Today we're talking about security, tokens, and wallets. And yeah, thank you for coming out today. I know you all received the announcements about classes being online and everything. We are recording it right now, and it's going to be available to you. But yeah, thanks for coming out anyways. My name's Janice. I haven't taught a lecture yet, but I'm basically the co-head of education with Minxing for blockchain at Berkeley. And I've been here since fall 19. I'm a junior studying computer science and cognitive science. And yeah, I'm excited to teach you about security, the first half, and then Minxing will talk about tokens and wallets. Okay, so let's just dive right in. It's just an overview. Okay, security overview. So why is public blockchain security hard? So basically, anyone in a public blockchain can call whatever functions they want and in any order they want. So any bugs or vulnerabilities are public. And the incentive structure is you ask users to find and exploit your code in order to earn the maximum gain. So why should you care about security? So immutable systems make it hard to exploit, immutable systems make it so that exploits are often very difficult to reverse the effects of, right? So on a blockchain, it's once something's done, it's done. It's really hard to reverse the effects of it. And without a legal system in place, security is the only thing that prevents network adversaries from destroying or bankrupting your protocol. So it's a very strong tie between the people you trust and basically your product. So let's look a little bit at the history. Has anyone heard of DAO before? No? Okay, yeah, Minxing. Yeah, DAO. So basically DAO is the Decentralized Autonomous Organization. It's a virtual venture capital, a VC fund that is governed by the investors of the DAO. So the main idea is that the token holders can become contractors by submitting proposals for funding of their project by using DAO funds. So basically, a contractor is writing your own smart contract and having that being a proposal. And if people vote on it, so if the proposal is approved by 20% of all tokens, then it will be submitted and it will be validated. So it transfers ethers automatically to the smart contract that represents the proposal. And actually they raised 12.7 million ether, which is equivalent to 150 million USD in June 2016. But then they got hacked. So they lost a ton of money. And the reason for this is because of something that was in their code. And it's called the split procedure. And that's the catalyst of the hack. The creators of the DAO basically implemented the ability of a DAO to be split into two. And this basically allows the minority, and basically minority people, or minority in that sense, are people who are able to retrieve funds when a proposal they objected gets approved. And they need at least 48 days before getting it into account you control. So there's a specific amount of days where you don't know where the funds that you invested in or that you proposed it is. And so that money is just in the cloud or somewhere. And so the hack happened because the coder found a loophole in this procedure. So once a split function is called, the code was written in a way where the ether can be retrieved and then the balance will be updated. So this was a problem. The problem was that the steps were just in the wrong direction in a way, because you retrieve the ether and then you update the balance. So what the coder did was they recursively call the split procedure and retrieve the funds multiple times before getting to the step where the code was checked. Basically, the code checked the balance. So the result of the hack was basically on June 16, 2016, the attacker retrieved 3.6 million ether, which is 150 million USD. And this is called the recursive call exploit. So another example we have is Parity, which is an Ethereum client that provides a web interface for underlying Ethereum node software. So allows the users to access the basic Ether and token wallet functions. And it's designed to integrate seamlessly with all the tokens, standard tokens, and manage Ether transfers. But basically what went wrong, right? Because the DAO went through all this hacking because of basically one split function. And the reason why parity got hacked was check permissioning. The attacker basically discovered that the default function routed all calls to the wallet library basically had a unpermissioned init wallet function, and basically allowed anyone to freely change the wallet ownership. So basically, you could change the ownership rights, and you're able to kill basically that wallet. And this resulted in a freeze of 573 wallets with balances of more than like 500K Ether. And that's like around 152 million USD. So basically, from these small errors in their code, people just the attackers found these small problems, and they attacked on it, and they got a lot out of it, right? Does anyone have any questions? Okay, next is attacks and vulnerabilities. So first is an overflow. Overflow is when a number gets incremented above its maximum value, and basically Solidity can handle up to 256-bit numbers. Incrementing by 1 would lead to an overflow, and that's seen in this picture. Underflow is the inverse case, where the number is unsigned. Decrementing will underflow the number and result in the maximum possible value, which is 255. And this OXF just means error, right? Okay, so let's look at the visibility overview. So there's public functions, first of all, which can be called by anyone, functions inside the contract, and functions from inherited contracts and outside users. External functions can only be accessed externally by other contracts, so it cannot be called by other functions of the contract, and it's not visible to the contract itself. And it's cheaper to use because it uses the call data op call, while public needs to copy all arguments to its memory. And then we have private functions, which can be called from inside the contract. And then internal functions, which is a more relaxed version of private functions, and the contracts which inherit from the parent are able to use this function. Basically, what you should get out of this is that you should keep your functions private or internal unless there is a need for outside interaction, or else there can be problems and hacks like the ones we've seen just now. Okay, so reentrancy attack. And this is a problem of spending before logging. So consider this scenario we have. I have $500 in the bank, right? And I ask the bank to give me $500. The bank checks and sees that my balance is sufficient, and they hand me $500. Then they deduct $500 from my balance, and I walk away happily. Does anyone see anything wrong with this scenario?
You can just keep calling it.
When?
Before the bank checks how much.
Yeah. And yeah, so this kind of correlates with the example we saw, right? So this is the scenario that can happen. I have $500 in the bank, and they give me $500 because they see that my balance is sufficient. They hand me $500. But I can recursively call, I ask the bank to give me $500, and it's still sufficient. My balance account is still sufficient. And I repeat this 100 times, and then I walk away happily with $50,000. So, and the bank just deducts $500 from my balance. And so this is the spending before logging error. And this is the equivalent code in Solidity, which you can just quickly take a look at. So basically, don't make this mistake. Okay, Solidity quirks. So there's randomness. So everything on the EVM, the Ethereum virtual machine, is deterministic. People have tried to use now and block.block hash for business logic in a contract. However, the results are very predictable, and it can be manipulated by miners. So that's bad. And there's another thing called timestamp dependence, which is a type of vulnerability, as it's not constant. So block numbers, and it's basically block numbers and average block time that can be used to estimate time, but this does not act as a future proof, as block times can change. So it's a type of vulnerability. So pragma statements is also something that you should be aware of. You have to make sure to lock your contract Solidity versions. New versions always come out, and it may introduce new vulnerabilities if contract isn't locked to one another. So this is dangerous because you adding the caret will have basically no breaking changes until like the updated version. So we can make sure that the code will compile in the way we intended it to be. So now, like, since there's a lot of like different hacks and a lot of attacks, there's a lot of tools that has been made in order to prevent that in a way. It's basically to analyze and like take steps to kind of like do semantic checking of code as shown on like the tweet on the right. So there's different tools that we have now, like securify.ch. It's like a static analysis tool for smart contracts. Hydra is a framework for like crypto economics, contract security. Porosity is a decompiler for blockchain-based Ethereum smart contracts. And then like Remix performs like static analysis to your code. So basically all of these are just does like analysis on your code to make sure there's no like vulnerabilities or like making sure that, you know, a hack will less likely to happen. So Open Zeppelin is an open source library, and it's basically helps you with writing secure smart contracts on Ethereum. So what kind of contracts are like available? There's ownership, which means that you can declare and claiming transferring. Safe math, which takes care of like the integer overflows and overdrawing. Push and pull, which is deposit and withdraw methods you can trust. And then you have like standard and basic like tokens like ERC20, which is implementable and ready out of the box. And you can check their open source and you can like use it as well on the go. Okay, mitigations and defenses. So what can I do towards security? Like what can I avoid to have like these hacks or like attacks and so on? So these are very simple steps. So first, like don't write fancy code. Code adversarially. The contract should take before giving. So we saw a lot of like the issues come up where we give before we like deduct or whatever. And so that's something that you should keep in mind. Use audited and tested code. Write as many unit tests as possible, as you should know in 61B, Simon. Prepare for failure at any moment in any contract or method. Roll out carefully, bug bounties before ICO, and keep the contract simple. Again, the more complex it is, the more attack vectors there are. And keep updating like with the software in the community. And of course, like beware of the blockchain properties like public versus private and send versus call and so on. Okay, so external calls. What is an external call? A call from one contract to another untrusted contract or account. And basically this can be done by like delegate call code, or call. And you could see that there's a lot of like bugs that happen, like the DAO hack and the Parity multi-signature wallet hack. So basically, you want to avoid external calls when possible and when it's not needed. Pull versus push. How do we get data and value to the address? So push basically contract transfers immediately to addresses after the logic, and this is potentially like vulnerable if the receipt contract is like poisoned. Pull is like what you want to use. It gives addresses the ability to get their data or money, and it's basically like a withdrawal function. Okay, assert and require. These are things you want to use like properly, and it's very good to use. So require condition is meant to be used for like input like validation. It should be done on any user, and it throws like a if condition if it's false. Assert condition also throws a condition if it's false, and should be only used for internal errors or to check if your contract has reached an invalid state, basically. So by following this, it will be possible like to use like a formal like analysis tool which verifies that invalid op call code can never be reached, and for the absence of errors and assuming valid inputs. So basically, it's checking like your required conditions and your assertion like the conditions as well. And then again, like rounding with int division. So all integer divisions, division rounds down to the nearest integer. It's basically like for precision and so on. And remember that all data is public. That on-chain data is public. Many applications require like submitted data to be private up until some point in order for it to work. If you're building on an application where like privacy is an issue, Basically, you have to like avoid requiring users to publish information like so early to make it public. You usually want to make sure everything is up to date and everything is safe before you make it public, right? So for example, you have like rock, paper, scissors. You require both players to submit like a hash of their move. So for example, I do like rock, and then Simon does like scissors and so on, and it turns to a hash. And require both players to submit their move. But I submit like something else, right? And if the submitted move like I chose doesn't match like my hash, we basically throw it out. Okay, two-party and party contracts. The main takeaway of this is that you have to be aware of the possibility that like some participants may just like leave or like just drop offline and you'll never see them again. So basically, you do not want to make like refund or claim processes dependent on a specific party performing a particular action with no other way of getting the funds back. Because if they drop out, like you can't contact them and you can't get those funds back. So you have to have alternatives for that. So for example, rock, paper, scissors, right? Again, a common mistake is that you like trust the other person that they won't leave or they'll make an action or they'll like pay or whatever. But the common mistake is that you don't make a payout until like they both submit a move. But how about if like one person doesn't submit a move, like just like drops out and goes offline kind of thing? So a solution is that you can provide a way of circumventing like participating participants, which is like have like a time limit or so on. And secondly, you can add like an economic incentive for participants to submit like information in all of the situations in which they are supposed to do so. For example, like deposit, stake, and slash. And last thing is always to remember testing. You always want to like test different scenarios and situations, as seen from like all the possible attacks and vulnerabilities. You always want to have like a 100% like coverage of like testing. And yeah, so now we have a security quiz. This will take like 5 to 10 minutes.
All right, then let's talk about tokens. So tokens is probably like one of the single most important application within cryptocurrencies. But let's first differentiate token with coins. Tokens are not a currency, so you don't need to create a blockchain in order to build a token. And coins are currencies like Bitcoin, which is native to Bitcoin network, and Ethers, which is native to Ethereum chain. So rather, the token is more like an entity with value associated with it. And most companies, when they perform ICOs, and now it's like IO or STOs, associate tokens as objects of shares of stocks of their company. So really, the beauty of tokens is that they can easily be built and have very standard smart contract logic behind them. And as we'll see later, it's really, really easy to issue your own token. So basically, you just need to fill in some ERC20 or 721 interfaces in order to issue your own token. So why do we need to build a token? Like, why is it useful at the first place? So the token can be used as symbols of values for smart contracts or dApps. It plays a vital role in the logic of these applications. So for example, for dApps, we take CryptoKitties as example. Each kitty in the CryptoKitty game is like a token. More specifically, it's a ERC 721 non-fungible token. And so you can issue your own token in order to better cater to the business logic of the smart contract. That's one use case. Another use case is that if you want to build your own blockchain-related project, you want to fundraising, you want to get money, and offering your own tokens is like one of the very useful, is one of the way to get money from the public. So the original way to do that is called ICO. Most people have heard about it, and now it has like bad reputation. No one is like using it, but it used to be really, really popular in like 2017. because the idea of ICO is really like IPO, and but since when ICO first came out in 2017, a lot of companies tried ICO and gathered a lot of money, and including some serious frauds. So gradually, like the public lose trust for ICOs. So instead of ICO, IO step in. So the difference between ICO and IO will be like ICO is just like any company, any individual can offering your own coins, and anyone can buy it, right? There's no intermediaries process to audit the legitimacy of this of the project you're participating. But IO is kind of different. So in IO, it stands for initial exchange offering. So there gotta be some exchange like Binance or Huobi or Coinbase, whatever name it. Those legit public exchange, they have to first like do some research of the project and audit your like the progress of the project, and if the team is actually is doing viable work. So through this process, after the exchange decided that this project is actually valid, it will put this project on the exchange. So anyone from the public can buy the token, basically. And the most serious way to getting token or issuing token is to SEO. So basically, every token is backed up by some physical asset, usually fiat. So that's like the most serious way of issuing a token. But today, most two popular ways to issue a token is either SEO or it's either SEO or IEO. Sorry, STO or IEO, my bad. So the cycle of token is as follows. First, you create it, then you can purchase, you can buy the token, right? Then you can transact with your tokens. So there are two categories of tokens. There are fungible tokens and there are non-fungible tokens. So first, let's talk about fungible tokens, which is like a question.
Yeah, what's an STO?
Oh, STO is like the basically every coin offering is backed up by a physical asset.
Oh.
Yeah. So it's like the most serious way for issuing a token. Okay, so let's talk about fungible token. So usually, okay, so one of the like the mainstream fungible token is it's called ERC20 tokens, which is a token built upon Ethereum, built on smart contracts, via the ERC20, which is the name of a protocol. So ERC20 tokens are a type of tokens standardized by Ethereum and can easily be built. This will also be the demo assignment for today. So you guys will build your own token via ERC20. And they're considered fungible since the one token will always be worth the same as any other tokens. Whereas ERC721, it's a different story. I'll talk that later. So all that is necessary to build this token is to implement the ERC20 interface, which basically you need to fill in like several functions. So let's actually take a look at the interface. So first is the total supply. So before issuing it, you want to specify what's the total supply of the token. And you want to specify the transfer from, approve, allowance, transfer, and approval. So the first three of them are some functions you actually implement. You just need to follow the interface. And these two will be the events of the contract. So basically, within each function, the functionality could be customized. But in order to actually issuing the ERC20 token, you have to follow this format, sort of, this interface format. And this is just an expansion of each function, each interface looks like, and some requirements of it. So we'll send the slides later. If you guys are interested, you can take a look at each specification. And there are some extra fragments. This includes some data structure you're using internally, like balances, and some mappings. You also need to specify the name of that token and the symbol. The symbol is usually, we use the symbol when we put the token on exchange. So usually it's like a 3-digit, it's like a 3-digit letters, like 3 letters.
TTC and ETH.
Yeah, something like that. And I think Janice talked about these two earlier, Open Zeppelin. You can also use Open Zeppelin to build your own ERC20 or ERC721 tokens. One advantage of using Open Zeppelin instead of using write everything from scratch by yourself is that all the libraries from Open Zeppelin is audited, so the security part is guaranteed. Otherwise, if you write them yourselves, you have to making sure there's no bugs or basically just I would recommend if you want to write your own smart contract or issue your own tokens, just use audited libraries like Open Zeppelin or Safe Math. Okay, so let's talk about non-fungible tokens. So one example of that would be ERC721, and it used to be the application of that used to be it used to be the most popular application in Ethereum, which is CryptoKitties. So are you guys actually familiar with it? Because it's a long time ago, 2 years ago, 2 or 3 years ago. Yeah, so CryptoKitty is basically a game for trading kitties. So they're those very cute virtual kitties, and each kitty is it's kind of like a card collecting game. So each kitty behind the scene is a ERC721 token. It is ERC721, not ERC20, because each different kitty will have different values associated with it. So what that means is different kitty, they will have different features or traits, right? So it could be hair colors or eye colors, right? And some features are just more scarce than others, and that usually means it's more valuable, and you can buy and sell kitties on an open market. So usually people sell kitties with rare features, and you can also buy 2 kitties and let them breed. So one case could be you get 2 common kitties have with common traits, right? And let them breed. There's a very slight chance that it will breed a baby kitty with some real traits or real features. So you can actually sell that baby kitty on the market. So in 2017, actually a lot of people play this game for the sake of making money, and yeah. So this game went viral in 2017. It even congest the transaction layer of Ethereum at the time. Yeah, and yeah, that's CryptoKitties. And followed by that, there were a lot of similar games. So ideas are the same, card collecting, and you can buy and sell those tokens. And here's a snippet of ERC721 tokens. Basically, the interface looks identical to ERC20. Okay, so we'll do a demo, and we'll go to a demo about how you actually create an ERC20 token and issuing it on the testnet later. But first, let's talk a little bit about wallets. So what is a wallet? So from high level, a wallet is just a user interface of users to manage tokens or cryptocurrencies, right? So a wallet would allow a user to first control access to a user's token. Second, manages keys and addresses. Thirdly, tracks the balance. And lastly, creates and signs transactions, right? So that's from the high level. But from a low level, a wallet is just a data structure that stores and manages users' public and private key pairs. And so basically, a private key allows sending money out of the out of the wallet, and a public key allows receiving money to the wallet. The transaction can be viewed on the blockchain using the public key. So for the security's sake, we want that for each transaction, we want to have so the most ideal case it would be for each transaction we want to have a different public key and a private key pairs. So that's like the vision when Bitcoin was designed in 2009. So how to achieve that? So first let's talk about like non-deterministic wallets. Well, that would be basically for each new transaction incurred or occurred. Basically, the wallet will generate a randomly generate a new key pair for that. But it has the advantage. The disadvantage includes that it's very cumbersome to manage and back up and import the keys, and also it reduces the privacy due to address overuse, like reuse, because it would run out of all the possible address at some point if we just like randomly generating a new private key. So one better way to do that is called deterministic wallets. So we will have a seed at the beginning. So these seed will be randomly generated based on some nonce, and so we can think this seed as some sort of master key, and these seed will generate like the first layer key, the second layer key, and each key is like derived from its parent key, sort of. So the advantage of that is the seed is sufficient to recover all the derived key. So when we want to back up the previous keys, we just need to store one key instead of storing all the non-deterministic keys. Question?
Why do you need to back it up? As in, like, how would you lose a key inside a wallet?
So basically, like, so basically, today, you log into a wallet through your address and your, what's it called, like some words basically like you chose, right? But within each account of your address, you actually have a lot of public key and private key pairs. So for example, take Coinbase as example. For each new transaction, you will have a new private key associated with them. And all these, so just for the security's sake, we want to back up those keys somewhere. So that's like one way to do that. Yeah. Right. So that's deterministic wallet. And we can even do better. So this is called like HD wallet. It stands for hierarchical deterministic wallets. So basically the idea is kind of similar to the previous one. It's just for each new key, it can generate a set of new keys. And via some like mathematical algorithms. So it's still deterministic, but it possesses additional structure. And it also makes the management easier. It gives access to a specific branch of keys, and users can create a sequence of public keys without having access to the corresponding private keys. So the cool thing about H3 Wallet is that for each single key pairs, basically the private. So for example, for this one, let's say this master key has a public key and a master public key and a master private key, right? And when we derive the master key into a child key, the public key, the public child key and the private child key will also be like corresponding to each other. Even these are like derived separately from the master key. So like that's like the core feature of HD wallets. It makes the management and the key storage a lot easier. And we also have multi-sig wallets. So this is just like, we can think it as a special kind of lock. You need to have 2 keys or even more keys together to unlock the lock. So basically, yeah, we need to have these things figured out before we specify a multi-sig wallet. But basically, the usage of multi-sig wallet would be first, you own some ethers and want to store security, but are concerned that just like relying on one single private key may not be safe enough. So you want to create a multi-sig wallet, but all the owners' accounts are under your control. That is like you're still controlling all the private keys, just like add another layers on security. Another use case would be you can like share this account with another person, right? So you set up a multi-sig account jointly owned by say 2 people, like you and Alice. So you have one private key and Alice will have another one. Only both of you presented the keys. You guys can use the fund basically. All right, so I'll go back to attendance later. So that's first. Simon, could you give them the GitHub?
Yeah, go to the course GitHub.
Okay. What's it called?
Go to blockchain at Berkeley. Search global. Search global.
I don't know.
Right there. You just typed it.
This one, right? So we have a contract here. So if you guys can all go to the GitHub page and download the contract. And since in the previous course we set up the MetaMask and we can just go to Remix and try to deploy this contract first. Okay. So yeah, one thing to mention is that this is not a good security practice.
So should we just like make a new file and copy paste?
Yeah, that'd be great. So as you guys are doing that, I'll explain a little bit about the code here. So this code is using the compiler version of 5.0. And this is some basically like safe mask API we're using just to guarantee the security part. And here is the ERC20 interface I mentioned earlier. So basically we'll be implementing all the interfaces here. And this contract is already being implemented. So what you guys want to do is you guys want to create your own token, right? So first, now I named this token like DDD, right? You can go here and rename it to just pick a name and name this token. Let's just call it BAP token. Yeah. And also, if you go to the constructor here, let's also change the name and the symbol. The symbol will be 3 letters. Okay, so let's talk about the total supply. So this will be the total supply in the units of weight for Wait, actually, I think this is like the not measuring weight. This is like basically stands for the basic unit for your token. Okay, so basically, this will stands for the basic unit of the token. So you can put an arbitrary number here. This will be the initial total supply of the token. And after that, if you go to MetaMask and find your account and copy the address and paste it to here. Okay. So, yeah, so basically that's all we need to modify in the contract. And then let's try to compile it. First, let's choose the correct version. And now it's successfully compiled, as we can see. And then let's choose our website provider. And let's choose BAP token. This is the contract we just compiled. And hit deploy. Confirm. Well, that will take a while. If we go here, we can see these transactions still pending, waiting for confirmation from the validators.
Can you go back for remit? Did you compile it? Yeah. What version? 4.5.
Okay, still pending. So that'll take a while. Okay, now it's confirmed. So now if you go to the contract, the address where the contract's created, we go to here, and in order to use our token, we actually need to verify it. So hit this button on either skin, and let's choose the compile type as single file because there's only one file, and the compiler version will be 0.5, and this should be like a license you're going to use for a token. Right now, for now, let's just choose no license. And hit continue. And then let's just copy paste the source code to here. Making sure to not optimizing it, because if you optimize it, the ABI and the opcodes will change, so it will not be mapping to our code. So hit verify and publish. Cool. So now this contract is actually published. And if you go to and this is a contract address, right? So copy the address. If you go to MetaMask and go to menu, you can add token. You can choose custom token and passing address and add tokens. Voila! Now you have this amount of that coin, and you can send it to your friends. So let's send to someone. I think this is Simon's. Simon's address. Okay. Actually, let's send more. Let's send Simon this amount of BAP coin and confirm. Yeah, so this is how you can interact with your customized ERC20 tokens. And this will also be today's checkpoint. Question?
Can you show how you get from remix to the verification for the new coin that you made?
Oh, so basically, when you deploy the contract, there's a Etherscan link here.
Yeah.
So if you just click it here, so this will display the transaction, right? And this row, the this row, it will display the address where the contract's created. And if you go here, you go to the contract tab, and you can see I just verified the source code. And if it's not there should be a button here named verified, and you can verify it. Yeah.